Orbital mechanics is the study of how objects move in space under the influence of gravity. Orbital mechanics focuses primarily on artificial satellites and spacecraft. While it's rooted in celestial mechanics, it specifically deals with human-made objects. The foundation of orbital mechanics lies in Newton's laws of motion and universal gravitation. Newton's law of universal gravitation states that every particle in the universe attracts every other particle with a force proportional to the product of their masses and inversely proportional to the square of the distance between them. Kepler's laws of planetary motion refine our understanding of orbits. These three laws describe how planets move around the Sun, but they apply to any orbiting body. Kepler's first law: planets move in elliptical orbits with the Sun at one focus of the ellipse. Kepler's second law: a line connecting a planet to the Sun sweeps out equal areas in equal times. This means objects move faster when closer to the primary body. Kepler's third law: the square of the orbital period is proportional to the cube of the semi-major axis of the orbit. This establishes a precise mathematical relationship between a planet's distance from the Sun and its orbital period. When a satellite moves along an elliptical orbit, its speed changes based on its position. This is a direct result of Kepler's second law. At the apoapsis, the farthest point from the primary body, the satellite moves slowest. As it approaches the periapsis, the closest point, it accelerates due to the conservation of angular momentum. To completely describe an orbit, we use a set of parameters called orbital elements. These define the size, shape, and orientation of an orbit in space. The two-body problem is a fundamental concept in orbital mechanics. It simplifies the complex interactions in space by considering only the gravitational attraction between two objects. This model makes several simplifying assumptions. Only two objects are present. They interact only through gravity. They can be treated as point masses, and no other forces are considered. While simplistic, it provides a remarkably accurate foundation for understanding orbital motion.
The two-body problem is a fundamental concept in orbital mechanics. It simplifies the complex interactions in space by considering only the gravitational attraction between two objects. This model makes several simplifying assumptions. Only two objects are present. They interact only through gravity. They can be treated as point masses, and no other forces are considered. While simplistic, it provides a remarkably accurate foundation for understanding orbital motion. Orbital mechanics becomes more complex when we consider perturbations, which are deviations from ideal orbits caused by various forces. In reality, no orbit is perfectly Capillarian. Various forces cause satellites to deviate from their ideal paths over time. These perturbations include gravitational forces from other celestial bodies, which can nudge a satellite's orbit slightly with each pass. For satellites in low Earth orbit, atmospheric drag gradually reduces orbital energy, causing them to slowly spiral inward. This is why the International Space Station needs regular boosts to maintain its altitude. Even sunlight exerts a force. Solar radiation pressure can significantly affect satellites with large surface areas, like those with solar panels. Orbital maneuvers allow spacecraft to change their path using engine burns, which apply thrust to alter velocity and consequently the orbit. One of the most efficient orbital maneuvers is the Hohmann transfer, which allows a spacecraft to move between two circular orbits using minimal fuel. The maneuver begins with an initial burn that places the spacecraft on an elliptical transfer orbit. When the spacecraft reaches the altitude of the destination orbit, a second burn circularizes the orbit at the new altitude. This two-burn maneuver minimizes the change in velocity or delta V required. Since rocket fuel is limited, efficient maneuvers like this are crucial for spacecraft operations. Gravity assist maneuvers, sometimes called slingshot maneuvers, allow spacecraft to change direction and speed by harnessing a planet's gravity. A spacecraft approaching a planet will be pulled toward it by gravity. As the craft swings around the planet, it gains energy from the planet's orbital motion. When the spacecraft departs, it follows a new trajectory at a higher velocity, effectively stealing a small amount of momentum from the planet. This technique is crucial for interplanetary missions. The Bepi-Colombo mission to Mercury, for example, uses multiple gravity assists from Earth, Venus, and Mercury itself to reach its final orbit. Orbital mechanics is crucial for numerous space applications. Satellite deployment requires precise calculations to achieve the desired orbit. Mars missions demand accurate trajectory planning. Engineers must calculate precise launch windows that occur only every 26 months when Earth and Mars are properly aligned. The International Space Station orbits at approximately 400 kilometers above Earth. It requires regular adjustments to maintain its altitude and avoid atmospheric drag that would otherwise cause its orbit to decay. Today, we're seeing exciting developments in the field of orbital mechanics. In-orbit servicing is emerging as a way to extend the life of satellites. The commercialization of space has led to more frequent launches. Companies like SpaceX are launching satellites at a pace never seen before. Reusable launch vehicles are reducing the cost of accessing space, making orbital operations more economically viable. Perhaps the most pressing challenge today is space debris. With over 27,000 tracked objects in orbit, managing this growing problem requires sophisticated orbital calculations and mitigation strategies. Looking to the future, advances in orbital mechanics will enable new possibilities in. This lecture will be about space exploration and utilization. As orbital space becomes more crowded, automated traffic management systems will become essential for avoiding collisions. We may see the development of interplanetary transportation networks, with spacecraft regularly traveling between Earth, the Moon, and Mars. Space-based manufacturing and resource extraction will rely heavily on precise orbital mechanics to position facilities optimally.